In this chapter, we are going to learn about nonlinear regression. Let's look at the what to-do list by Cargood and Stern when the linear regression assumption appeared to be violated. And one reason for this violation could be due to a wrong assumption of linearity in the association between outcome and exposure variable. Okay, and let's look at next example. When you see data like this, okay, and this could be indicating association between age and systolic blood pressure. Okay, and then popular method of nonlinear regression is you simply introduce product term of age. So here I put the square term of age in equation. Okay, and if the association is nice convex, and this formula will pick up this nonlinearity by assessing effect of this this square term. And okay, so to do this in the software, you can create a new age variable, age 2 for example, and which is age times age, and then you include age 2 as a new variable in equations. Okay, so it's easy to do this type of nonlinear. Or another choice is you might do exponential of age. So if the association is exponentially increasing effect by age, and this nonlinear regression will pick up association nicely. Or you could do log, and if the association looks like this type of nonlinear, and then you can do curve SPP equal log of age. Okay, so this is SPP equal exponential of age. Right. So there are lots of nonlinear functions, and you can fit instead of linear function. Although the disadvantage of using this pre-chosen formula is if you have data looks like this, and you don't really know what type of nonlinear function would fit this association. Okay, and if you choose polynomial of second degree, or exponential function or log function, when the true association doesn't fit those a priori specified form, you can bias your study result. So it would be nice if you can do nonlinear regression without assuming form of association. And popular choice of nonlinear regression, especially non-parametric nonlinear regression, is a low-S regression. And low-S regression is locally weighted scatter plot smoothing regression. And the idea is that for each observation is when you fit this smooth nonlinear line, and each observation is fitted to a separate linear regression line based on adjacent observation. Okay? And these points are weighted so that the further away the x value is from the point of interest, the less effect it has on determining estimate of the point of interest. The proportion of the total data set considered for each data points of interest is called the bandwidth. So let me show you our simulated data. If you do linear regression, and what will happen, and you use all of the observations, okay, and then you put the linear regression straight line, and so that distance from each observation to regression line is minimized. All of these data points are contributing to draw this one line. Okay? And instead of doing that, what we do here using LOS is, okay? And for example, if you want to estimate the curve here, this is a points of interest. Okay? And you first set the bandwidth. Right? So within this bandwidth, and you wait mostly on the observation which is closest to that point. And further away observation is, you wait less. And by doing that, you draw one straight line here. And you do the same thing on all data points. For example, here, determine bandwidth, and then you fit straight line, although, okay, with the weighting, biggest weight to closest observation and least weight to the furthest observation within the one bandwidth. So if you repeat this process, okay, so you do this for all data points available, okay, and so you fit straight line here, you fit straight line here, 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 okay, and eventually you will smooth those lines. Okay, so this is how we do LOS. It's easy enough. So, smaller the bandwidth, okay, and you can create the bumpier looks graph. So this is a LOS when bandwidth is set to 0.1, and this is a LOS when the bandwidth is set to 0.7. Okay. So you see, as bandwidth increase and smoother the line become. SPSS, and you can do this LOS by double clicking on the graph, and click on this icon, and same icon when you do linear regression. So this will do linear, and this will do quadratic, and this will do cubic. And so you can do nonlinear and LOS, okay, and I set the bandwidth of 50, okay, or 70. This is the same as 0.7, 70%, okay, or 80%, okay, and so you can do LOS. And so if you set the bandwidth lower, and the graph become a lot bumpier. So SPSS does have a feature of doing a nonlinear curve, although there are the disadvantages using SPSS for nonlinear regression. And we cannot include more than one independent variable in an equation, so we can't adjust for confounder. And then also it works only for continuous outcome variable, so you can't really do nonlinear effect for logistic regression or other type of regression than linear regression. Right? So my recommendation is contact statistician when you want to fit nonlinear effect in your analysis. I will introduce you to the method we use called the restricted cubic spline. Okay, so here, restricted cubic spline, as you see, the combination of three terminology. Okay, so let me explain one by one. And word spline. Spline is a thin wood or metal strip used in the building constructions. Okay, and the word cubic comes. We actually fit cubic polynomial function within each interval. 1, 2, 3, 4 areas separated by 3 knots within each area, and you fit with polynomial, cubic polynomial functions. Okay, And the word restricted come in order to avoid influence by sparse data or outlier, and we force to have linear regression, linear line, and for both areas in the very right and then left areas. And we can specify number of knots. So this graph we cut by 3 knots, and you can cut by 4 knots, 5 knots, 6 knots, and 7 knots. When you cut by 3 knots, and the knots are placed based on distribution of independent variables, and these are percentiles. So you place the knots on 10s, 50 median points, and 90th percentile points with 3 knots, and 4 knots, and it would be 5th percentile, 35th, 65th, and 95th percentile. Okay. So these are a priori decided. And the more knots you put, and you can make graph bumpier. Okay. So this is an example looking at effect of mean arterial blood pressure on length of hospital stay. And 5 knots are placed. Okay. So 2 end areas, associations are forced to be linear. But the areas in between, and polynomial, cubic polynomial function were fit. Okay, so this is a technique we use in our practice. Right. So next 10 minutes or so, I want to show you demonstrations of our software in fitting nonlinear regression. In this exercise, we are using data from Framingham study, and we will compare linear regression and nonlinear regression, and on the association between age on serum cholesterol level, and also BMI on systolic blood pressure. And we will use 2 packages. One is RMS and one is foreign. So let's load these 2 libraries first. Okay. So I set up this code so that you can simply cut and paste on our lines, and you can execute this code. So let's cut and paste, copy and paste, and okay, so we loaded 2 library and paste. It has a warning, so let's make sure dataset is red. Okay, yes, it seems okay, and let's move on. And R has very useful function called the describe, and if you copy and paste, okay, so now you can see what variables are in the data set, and you can see descriptive data for each variable. So we have systolic blood pressure, and there is total of 46,099 observation, and there is no missing, and there is 116 unique value. Mean of systolic blood pressure is 132.8, and 5th percentile is 104, and 90th percentile is 162. And you can examine lowest 5 data points and highest 5 data points, and this is useful when you check data errors or outliers. Okay, so we have a systolic blood pressure, we have serum cholesterol, and we have coronary heart disease, age, BMI, and ID. And important things when you look at an ID, and let's make sure there's no duplicates. So there is 4,699 unique numbers for same number of observations. So there's no duplicate in this data. That is good. And then we have a variable showing a gender of a patient. In Framingham study is prospective cohort study, so they have a follow-up years as well. Okay, and data density is very useful functions, and you can visually see the distribution of each variable. Okay, and so this is the low S, and low S we use a function called PLSMO, and this is a variable you want to place on x-axis, and this is the second variable will be placed on y-axis. And when you set the true for data density, and R will plot these bars. A longer bar present where you have more higher density in data. That means you have more observations here than these two ends. So, okay. So if we check that with data density, this is a distribution of age. OLS stands for ordinary least square. This is the method you draw lines so that distance from each observation to regression line is minimized. Okay? And SCL is outcome variable and age is independent variable. And after we run linear regression, we placed a result into the object and named F1. So I just pick arbitrary name and put it F1 as function 1. Okay? And if you want to see result of this regression in graphical form, you can use a predict function and plot function. Okay? And next function ANOVA provide a p-value. So the p-value next to age show if the age is statistically significantly associating to serum cholesterol level. Okay, and next line is the same OLS, but you now look at nonlinear association between age and serum cholesterol level. To do nonlinear effect in R, which is very easy. So we use the same function OLS, and all you have to do is place RCS, stands restricted cubic spline, and before age, and you do parenthesis age, comma 3. 3 is the number of knot you want to place. Okay? And the p-value for nonlinearity is less than 0.001, which is highly significant, and there is overall effect of age. So we can say association between age and SLI is statistically significant, and it was nonlinearly associated. And another table provide the p-value we just saw in the previous graph. Okay? So the p-value next to age indicate overall association, effect of age on serum cholesterol level, and the p-value next to nonlinear, and this indicate if the nonlinearity is statistically significant or not. And next, we do similar regression, nonlinear regression, to assess association between BMI and systolic blood pressure. Okay? And here we allow effect of BMI to be nonlinear, although the graph looks very linear. And so if you check the p-value for nonlinearity is 0.4425. And although there is overall effect of age, that effect seems not nonlinear, so that may indicate linearity. Okay? And when you do ANOVA parentheses, the name object, you store the result of this regression. Okay? And you can see the p-value for BMI and p-value for nonlinear effect. And as you see, examining nonlinearity using R is very easy. So we are more than happy to run the nonlinear regression for your data. So please do not hesitate contacting your local statistician.